Hello everybody, Dr. Matt Ed. Today we'll talk about pressure recovery and echocardiography. Objectives: to define pressure recovery and understand its physiological basis, differentiate between echo-derived and catheter-measured gradients, understand the types of energy and blood flow. Just a quick refresher, blood has three key energy forms, and they're pressure energy, kinetic energy, and gravitational energy. The gravitational energy is negligible, so we'll just ignore that. Pressure energy is also known as potential energy, static pressure. It is the energy or the pressure that's against the walls exerted by the blood. Kinetic energy is movement or the dynamic pressure, and it's the direct force from the velocity of the blood, so the pressure forward. And total energy is conserved, so total energy or total pressure equals static pressure plus dynamic pressure and plus the gravitational potential, which we said was negligible. So if velocity or the dynamic pressure increases, pressure or the static pressure must drop. Next, we'll talk about the Bernoulli principle. As blood speeds up through a stenosis, such as the aorta or the aortic valve, the pressure will drop. By the Bernoulli equation, it is the change in pressure equals 4v squared. And this calculates the peak pressure drop, which is not the true net loss because of pressure recovery. And we'll explain this in the following slides. What is pressure recovery? After a tight valve, the blood flow slows down, and some of that kinetic energy is converted back into pressure. And this recovered pressure makes the net gradient smaller than what the echo shows. That is because the regained pressure is not captured by echo Doppler, so echo will overestimate the pressure drop across the valve, whereas pressure recovery is captured on cath. And this is important in small aortic roots. In small aortic roots, the reconversion of energy is more efficient because the flow stays more focused in the center. This causes a larger fraction of the high velocity kinetic energy to be converted back to the static pressure. But in a large aortic root, there's a lot of turbulent flow and wide dispersal of energy, which causes waste, and that energy you don't get back. So the smaller the aortic root, the more significant the pressure recovery. So the echo Doppler measures peak instantaneous gradient across the valve based on the highest velocity, whereas the cath measures peak-to-peak gradient. That's before and after the aortic valve. And because of pressure recovery, the cath numbers, the pressure gradient, is often lower because they get some of that pressure back. So the difference between before and after is lower. So the takeaway here is echo may say that there is severe AS because of higher gradient, but cath may say it's moderate, and the difference because of the pressure recovery. Here's a case example: 75-year-old woman where the echo shows a peak gradient of 70 millimeters per mercury and a mean gradient of 45 millimeters per mercury. The aortic valve was calculated to be 1.1 centimeters square. Here the cath shows a peak-to-peak gradient of 25 millimeters per mercury, and the discrepancy in the pressure, the peak gradient or the peak-to-peak gradient, is due to pressure recovery. In summary, blood flow energy equals pressure plus kinetic, and according to Bernoulli, if velocity increases, the pressure must decrease. Echo calculates pressure drop from velocity, so it measures the pressure recovery, and cath sees the true net pressure difference. Thank you for watching. If you thought this video was helpful, please like, subscribe, and watch out for my next video.